I'm going to study and discuss about the classification of modes of ventilation in terms of a scientific taxonomy. So, all of the intensivists, when we are dealing with mechanical ventilation, we are dealing with these things on a day-to-day basis. We use various terms like controlled breath, spontaneous breath, assisted breath, supported breath, and then we have various modes. So, it's not always clear what exactly we mean by this and how to look at these ventilator variables, ventilator modes, and the type of breaths in a scientific manner as described. So this presentation is heavily based on the description of the modes of ventilation taxonomical classification given by Robert Chadbourne in 2014. So let's go ahead. What is a mode? To describe a mode, it's a predetermined pattern of patient-ventilator interaction. How the patient and ventilator are interacting with each other. It has three basic components. That's all we need. We need these three basic components to completely classify or give a tag, the taxonomic attribute grouping to a mode. These three components are the ventilator breath control variable, that is the first. The other is the breath sequence. What is the type of sequence the breath, which type of sequence the breath is being delivered. And the third is the targeting scheme, how the ventilator is modifying its the giving the output, the feedback as to what we have set and what is the ventilator, how is it using those parameters to give us an output. We'll look at the examples in detail. So basic thing, we have ventilator breath control variable. What we mean by this is as per the equation of motion, it's quite clear, it's very basic, that at one time the ventilator can control only one part of the equation of motion, either volume or pressure. Then the second part is the breath sequence. So there are three types of breaths: continuous mandatory breaths, intermittent mandatory ventilation, continuous spontaneous ventilation. And then we have various targeting schemes: set point, adaptive, servo, optimal, intelligent. All of these combined give together a mode. If we define all these parts of a breath, then we know the type of mode and what this mode is exactly doing. And this also gives us the ability to compare modes between the various brands. So the same mode may be available with various names in various brands, but this mode may be, if we know that these technical concepts, then we know what exactly is that mode doing on the patient. So the ultimate purpose is to demystify various terms, various modes. We have various modes, and we not don't always sometimes same mode is there on the same different brands, or we think that the mode is simple, although it may be more complicated than we think on the on a first uh, thought overall look, the first look. So Chadbourne had described the 10 maxims of ventilator classification taxonomy. The initial 4 or 5 breaths maxims are pretty basic, describing what is the breath, how the breath is assisted, whether the ventilator, how the ventilator controls the, what is the parameter, either it can control either pressure variable, how the breaths are classified, what about the trigger and cycle events. Then in the last 10 parts comes the application and condensation of these initial parts, where the difference comes from the conventional teaching or the conventional understanding in terms of where we try to specify spontaneous and mandatory breath, the breath type, and the three basic sequences and and then we combine these two to give them what we get is the five basic ventilatory patterns. Then ultimately comes targeting scheme, which leads to more complexity. Various combinations are possible. We'll look at some common examples in the brands that we use on day-to-day basis and ultimately try to classify some modes. And then we'll see some examples how some modes are exactly the same in different brands. Initial few maxims I'll go faster, pretty basic. We're trying to define a breath. First is definition of breath. Breath in terms of flow time curve. Here is inspiratory part, this expiratory part. So one cycle of positive flow is inspiration. This is negative flow expiration. Total cycle time is the sum of the I time and expiry time. Total cycle time is one by frequency. So if you have say around 20 breaths in 60 seconds, so one cycle time will be 33 seconds. So inspiratory expiratory ratio is defined as the ratio of inspiratory time to expiratory time. That is pretty basic. Duty cycle is also pretty basic. Percentage inspiration, the ratio of the inspiratory time to total cycle time. So if your total cycle time is say 23 seconds, T total, then your inspiratory time, say if you're in 1:2 configuration, so 1 second will be, so out of 3 seconds, so 1/3 will be the duty cycle. Tidal volume is taken as the integral of flow with respect to time. So in other words, the I time in these modes can be defined, derived by this division of tidal volume by the flow. And for constant flow, inspiration nearly equals the product of flow and the inspirated time. These are the initial essential basics of how these things are delivered. These parameters are delivered. Second is regarding the assistance. So breath is assisted if ventilator is providing some or all of the work of breathing. The ventilator does some part of the work. The work is defined in terms of the trans-respiratory pressure with respect to inhalation volume and the loaded breath, and there may be a slight supported by triggered breath. So a loaded breath is a breath, for example, where the trans-respiratory pressure decreases below baseline during inspiration. So what happens is, suppose a flow or pressure triggering, that is a normal, say, routine assisted breaths. Here the patient initiates, but ventilator will quickly provide an inspiratory support. So the key will be that the airway pressure will rise above the baseline once the ventilator starts delivering the flow. If you have set the flow poorly or it is insensitive, then it can become a loaded breath. But suppose the trigger threshold is too high, the patient will pull a lot of airway pressure below the baseline or divert a large fraction of the bias flow before the ventilator starts to cycle, give the breath. This type of breath would be known as type of a loaded breath, inspiratory loading. So if patient is totally paralyzed by, say, neuromuscular blockade, then they will be fully supported by the patient. The ventilator will be fully supporting. And typical unassisted breath will be a ventilator is simply providing flow as per the patient's inhalation demands. Typical example is a CPAP with a demand valve. But important thing to note is assistance is the term is attributed to by the patient effort. It is not a type of breath. We'll look at this in further slides. Basic equation of motion is pressure, volume, and flow as continuous function of time with parameters of elastance and resistance. Pressure over time is equal to the product of elastance into volume as a function of time plus resistance into flow as a function of time. So if one function is predetermined, the other two can be derived. So control variable is the function which is controlled during a breath, inspiration. So at one time, either pressure or volume or flow can be controlled. So this form of the equation assumes that patient is not making any inspiratory efforts and expiration is totally complete. There is no autopay. For example, in volume controls, so for both flow and volume, if you want to classify a mode as a volume control, then we should be able to set both flow and volume. Setting, if we are able to set, suppose tidal volume in a mode, but flow setting is not there, so that technically that mode cannot be classified as a volume control mode. We'll see that the example is a common mode in which we are able to set a tidal volume, but that mode is not a volume control mode. So in volume control, this maximum 3. For volume control, both volume and flow are preset prior to inspiration. Setting tidal volume, not sufficient. So some PC modes will allow us to set the target tidal volume, but they allow the vent to control the flow. That's what I was talking about. That is adaptive targeting in PRVC mode. Setting only flow is also not sufficient because some pressure modes will allow us to set a maximum inspiratory flow as well. But tidal volume depends on the inspiratory pressure target. This pressure control CMV, pressure control SIMV. These are examples of that we need to set to classify as a volume control mode. Both volume and flow should be preset, should be in our control. For pressure control, inspiratory pressure as a function of time is predetermined. A particular pressure target may be set or inspiratory proposed pressure may be proportional to the patient effort, even in a pressure control mode. This is some various, for example, the modes of neural and disturbance with resistance, now and system inflation plus PV plus, where the pressure is in proportion to the patient effort. The pressure rises in real time proportional to the neural drive. In CAV plus, if the pressure is proportional to flow and volume, which is described by gain. Pressure waveform itself is actually continuously modulated by effort in these modes. These are a type, this targeting scheme is a type of servo targeting. NAVA is a classical example of servo targeting. So time control it can be another mode technically. This will be a mode for which inspiratory flow, volume, and inspiratory pressure all will be dependent on the respiratory system mechanics. So here No parameters of pressure, volume, or flow are preset. Only breath control factor here is the timing, inspiratory and expiratory time. So one example of here, which could be in the HFOV 3100 ventilators, here we set the frequency, I time, and amplitude. So here we are setting frequency, which determines cycle time. The I to E ratio is determined by the I time, amplitude, delta P. Here the ventilator does not target tidal volume or flow directly. Here tidal volume again will depend upon the oscillation amplitude, the frequency, and the lung mechanics and compliance and resistance. So that's why it is considered time controlled ventilation. Here the ventilator cycling between inspiration and expiration based on a preset timing variable, not on the patient's effort or volume or pressure targets. So oscillator frequency, that is the frequency that we have said, that is the main ventilator, that is the main primary control variable. Ventilator does not technically wait for the patient effort, so there is no not patient triggered. So it does not target, because it is not targeting a set volume or pressure per breath. Instead, this amplitude and I time shape how the oscillatory waveform works, and the cycling happening because of the time I time. Therefore, it can be taken as a type of a time controlled ventilation. So even though we are setting a arterial mean airway pressure and amplitude, the defining control variable for cycling here is frequency. That is why it is classified as a time controlled ventilation. This is in contrast to the conventional modes like pressure control, where cycle ends. Conventional pressure control, where cycle ends when the time expires, so pressure is the primary control variable. In conventional volume control, where cycle ends when the time expires and volume will become the control variable. So in HFOV, cycle is centrally determined by frequency, and pressure swings are secondary modifiers, not the main cycling determinant. Second, the fourth maxim is classification of beds. So breaths are classified according to criteria which trigger, start, or cycle the inspiration. Now in comes the slightly technical parts. The inspiration starts triggered by a variable, basic trigger variable, which is a preset breathing frequency. Then monitored variable, that's a trigger that then achieves a preset threshold. So it may be a classic basics of the most basic trigger is the time, the preset breathing frequency. Suppose we are on a pressure control assist control mode, so a patient is paralyzed. We have set a frequency of 20, so every 3 seconds the breath will be delivered. That will be a mandatory time controlled breath, mandatory breath. So this will be a time controlled, time triggered breath. Other trigger variables that we know are can be minimum level of minute ventilation. It may be a preset apnea interval on various modes, or it may be various indicators of inspiratory effects like changes in the baseline pressure or electrical signals of the diaphragm movement. So some examples of various this type of triggers are minimum level of minute ventilation becomes a trigger in a mode called mandatory minute ventilation. Here, this mode tries to ensure a preset minute ventilation by adding mandatory breath if spontaneous effort falls short. A preset apnea interval, suppose you are on a BiPAP or a CPAP, the backup rate. So in an IV, servo I apnea ventilation, these all switch to control mode after the preset apnea ventricle is suppose elapsed. Then indicator of inspiratory effort in pressure support ventilation, pressure control SIMV, volume control SIMV. There may be flow or classical, the basic flow or pressure triggers that we set the conventional modes, the commonly used modes. And suppose electrical signals of the diaphragm in the this is a neural drive measured by the diaphragm EMG, the eddy. The ventilator will delivers the assistance in proportion to the effort. This is the NAVA. Here, pressure waveform is proportional to eddy signal. So these are the other types of trigger variables. It's moving ahead. Inspiration cycled off when a monitored variable cycle variable achieves a preset threshold, that is cycle event. This also becomes what is cycling the breath becomes a limiting, a defining feature of how we differentiate between mandatory and spontaneous breaths. We'll look at in detail these examples. So simplest cycle variable is the preset I time. So the initial example, patient is sedated, paralyzed. So you have a certain I time of per breath. You have a 3 second per breath, suppose. So after a certain I time, the period is elapsed, then the inspiration will cycle off and you will go into expiration. Other cycle variables can be pressure. Suppose you are in Holter mode, there was in pressure cycling here. Suppose suddenly pressure rises to a very high limit, Pmax is reached, and the patient will cut off the inspiration and will go into expiration. Then cycle variables can be volume, volume control modes, all sorts of modes. Basically, volume becomes cycling variable, and flow, percentage of the peak inspiratory flow in some modes, that it may become cycling variable. Typical example is a pressure support ventilation. When certain level of inspiratory flow has dropped off, you go into expiration and multiple signals of breath can also be cycling away. Now, these trigger cycling events, they can be patient initiated, ventilator initiated. Now we are coming to inspiration. So baseline airway pressure changes can be by patient or patient signal, cycle change, baseline flow, patient signal, patient and pressure and flow triggering both are patient triggers. Ventilator trigger is after a certain time has elapsed, independent of patient trigger signal already discussed. Now coming to cycling, same thing we have already, I've said it. Patient cycling is ending I time based on signals representing the patient determined components like elastance, resistance, and including efforts. And flow cycling is the type of patient cycling because the rate of flow decay to the cycle threshold I time determined by the patient mechanics, the time constant and the effort. This is the this type of cycling happens in a pressure support mode. Ventilator cycling means ending the inspirated time independent of signals representing patient-determined components of equation of motion. For example, in pressure controlled continuous mandatory ventilation, passive or either passive or active, it will always be a mandatory breath here. With volume control CMV, passive patient HFOV, PRBC. So this is a conceptual situation that volume control breaths, why they are considered cannot be mandatory because volume control breath are not spontaneous breath. Even though pressure rise is determined by patient mechanics, volume control CSV is not possible. We'll see once we are looking at the breath sequences again. These are trigger and synchronization windows. Trigger windows are the is a window at the end of inspiration. There is a trigger window. There's after a small refractory period, there's a trigger window during which the patient can suppose trigger another next inspiration, and synchronization window are given at the end of expiration. There is a synchronization window where the patient ventilator will wait for the patient to give a signal so that it can try to synchronize it's the mandatory breath which is coming with the patient signal. So this will give rise to a synchronized breath, but it will be a mandatory breath. So this is a synchronization window short period. So this is how these work. Some ventilators have a synchronization window at the end of inspiration as well, where the patient signal can be used to cycle off inspiration and go into expiration. So what happens during synchronization is the patient signals occurs during an expiratory time. Suppose here synchronization window, inspiration starts, and the ventilator triggered event gives a mandatory breath. This is considered a mandatory breath and not a spontaneous breath because in if in even if patient had not triggered, the ventilator was going to give a mandatory breath anyway. So that's why it is described as a synchronized breath, but it's a mandatory breath. Now coming to the main things which we have been repeating again and again, how a breaths are classified as spontaneous or mandatory based on the trigger and cycle event. Spontaneous breath basically means the patient retains control over timing, start and end of inspiration. It is determined by so these things are determined by that patient, independent of any ventilator settings of inspiratory and expiratory times. Patient for a spontaneous breath must both trigger and cycle the breath. This is spontaneous breaths. Now they may be assisted or unassisted. The assistance here described is in terms of the trigger and the support provided. This is not a type of assisted breath. It's not a type. It's a type of subtype. You can say subdivision of spontaneous breath. So assisted or unassisted. For example, CPAP may be unassisted. Pressure support is assisted spontaneous breath. A mandatory breath is a breath over where patient has lost control over timing, either rate or inspiratory time. If the patient cannot cycle off on his own, and if the cycling of variable is determined by the patient, suppose by the ventilator, then that breath by definition will become a mandatory breath. So start or end of inspiration or both, if they are determined by the ventilator, independent of the patient, that becomes a mandatory breath. And mandatory breaths by definition, as ventilator is controlling pretty much all of the variables, it is by definition an assisted breath. So spontaneous breaths may be both assisted and unassisted. For spontaneous breath, patient should retain control over the ventilator breath size and breath time. That is important. So in this table, let's look at it again. So in a mandatory breath, ventilator in suppose in terms of trigger, it will really be a time trigger. Patient effort, if it happens, it can be inside a synchronization window. Then that will ventilator, if that ventilator will align that breath with the patient's mandatory breath, the ventilator would have delivered it anyway, so it becomes a mandatory breath. In a spontaneous breath, patient triggered and cycled, patient effort alone will initiate the inspiration and no preset ventilator schedule forces a breath. How it is being ended, that is why extremely important. How the ventilator cycling. So preset ventilator in mandatory breaths turns off the inspiration after preset inspiratory time. Patient effort inside the synchronization window again may align with the cycling. Suppose at the end of inspiration, there is a synchronization window. Then this may align with the ventilator, but the ventilator would have cycled regardless. So that is also considered a mandatory breath. In a spontaneous breath, the patient's effort determines the flow cycling. It could be neural signal or it could be a flow decay. Because the flow decay depends on patient's lung characteristics. That's why it is will be called as a spontaneous breath. Control of timing. Patient here loses control of timing. Even if it's synchronized, ventilator will enforce the frequency or the I time that we have set. Here in spontaneous breath, patient can breathe for as long as he wants. That will be a retained control, full control of timing, start and end. Label, we call this breath as a mandatory breath, even if it is synchronized with the patient effort. And a spontaneous breath is the other way, where patient has full control. It will be assisted and unassisted. Examples will be pressure control CMV in a passive patient. Here we'll get time triggered, time cycled, classical mandatory breath. In SIMV, the mandatory breaths are there along with synchronization windows. In APRV and correspondingly, pressure support ventilation is a classical example of spontaneous breaths where we only get spontaneous breath. These are patient triggered, flow cycled, and maybe assisted because this assistance is decided by the level of pressure support that we set. NAVA is a patient triggered, patient cycled via the eddy. That is also a spontaneous mode. Um, then APRV is pressure is the mode where you have a certain time of T high at which high pressure is being applied during the inspiration, where there is a very short T low. For the T low, which is 4 to 5 seconds, there is some pressure releases. But these releases that we had that happen to a low pressure during T low in APRV, these are mandatory breaths. But patient has the ability to breathe either during inspiration or expiration. So these are considered spontaneous breath. These spontaneous breath in here, patient can breathe on his own. He can get some flow as much flow as he wants, and this breath may be for as long as he wants. These are on top of the mandatory breaths. So in APRV, you have both type of breaths: mandatory breaths and spontaneous breaths. These are some modes where only suppose spontaneous breaths are possible, like CPAP. CPAP is a typical unassisted spontaneous breath. Here, patient breathes spontaneously at a constant baseline pressure. There is no inspiratory assist, just a pressure support or PEEP or CPAP. PSV is it's assisted spontaneous because a patient can breathe as much as he wants, but there's pressure supported. NAVA is assisted spontaneous because in proportion to the patient's electrical significance, some inspiratory pressure in proportion to the national drive is being provided. Proportional assist ventilation plus PAV plus is also a spontaneous mode because patient effort, flow, and volume will determine the inspiratory pressure in proportion to the mechanics. Ventilator will amplify this effort by giving some assistance. This is assisted spontaneous. Volume support is also an assisted spontaneous. Here, patient will trigger each breath. Ventilator adjusts pressure support to try to reach that tidal volume. Auto mode is the patient is breathing spontaneously. When assisted spontaneous, it's servo I. It will automatically switch from pressure support or volume support when patient effort is present and no mandatory breaths are delivered. This is advanced mode, not very commonly used, I think, or don't think. Spontaneous modes in BiPAP and CPAP devices can be assisted or unassisted spontaneous type of breaths. Here, patient usually controls timing. Ventilator provides baseline pressure and optional support. Now let's come to the breath sequences. So we have three basic breath sequences: continuous mandatory, intermittent mandatory, and continuous spontaneous. This particular pattern of breath. In continuous mandatory ventilation, we also known as assist control, spontaneous breaths are not possible. Every patient trigger will produce a ventilator cycled inspiration mandatory breath. Now this line suddenly comes out to you that would you would want to think what does that mean. So continuous mandatory ventilation assist control, what we are saying is that spontaneous breaths are not possible, but patient can trigger. That is where the understanding that we have to understand that pressure control, assist control, all these common modes, these are suppose even if patient is triggering. Suppose you have set PC SIMB and there is no SIMB. It's only PC assist or volume control assist control. This is a continuous mandatory ventilation because patient may trigger as much as you want. There may be total respiratory rate will go above the set rate, minimum set rate, but each and every breath which is triggered by the ventilator will be identical to the time cycle or time triggered breath that we have set, the parameters that we have set. So every patient trigger produces a ventilator cycled inspiration. That's by definition because the timing, characteristics, everything cycling is controlled by the ventilator. This by definition becomes a mandatory breath. This is a continuous mandatory ventilation. In intermittent mandatory ventilation, spontaneous breaths will be possible apart from the mandatory breaths, different. So different breaths, some other breath may be a spontaneous breath. There are three types commonly. So mandatory breaths, IMB type 1 is mandatory breaths are always delivered at set frequency, say SIMB volume control. You see in a, say in a Puritan Bennett example. So you have SIMB volume control with SIMB pressure support, suppose. So some there will be a mandatory breath that we have set will always be delivered, and some extra breaths will be synchronized with the ventilator. IMB2 is where mandatory breaths are delivered only if the spontaneous breath rate falls below a set frequency. This an example of this would be a ST mode in a BiPAP or Respironics V60 ventilator in the BiPAP mode on this ventilator. Suppose spontaneous breath rate falls below a set rate, then mandatory breaths will be delivered. So here spontaneous breath will be able to suppress mandatory breaths. And IMV3 is mandatory breaths delivered only if the measured minute ventilation drops below preset threshold. This is limited to a particular mode, like a mandatory minute ventilation mode on drag or on adaptive support ventilation on Hamilton. Here, mandatory breaths will be delivered only if the measured minute ventilation drops. So ultimately, let's comes to this combining all this. So we have two control variables, pressure or volume. We have three sequences, CMV, IMV, CSV. So combining this 2 and 3, we have 5 patterns, basic patterns. So we have volume control CMV, we have volume control IMV, then we have pressure control CMV, pressure control IMV, and pressure control CSV. Volume control CSV, you might think why it is not possible, because for volume control, cycling by the patient has not has lost control, because cycling is always done by the ventilator, because the inspiratory time, once this volume is set, it will change to expiration. Even if the patient wants to breathe more, get more flow, it is not possible. So patient has lost control over the timing and the size of the breath. So by definition, for VC CSV is not possible. So these are the 5 basic sequences. Now comes the basic in quickly we'll look at the targeting schemes. So we have 5